Under this was stationary waves produced in one-ended open organ pipe or air columns. The other end is closed, right? So introduction, you can go for, can you see the slide presentation?
Yes, ma'am.
Okay. Was introductory part, you can follow the previous one. So the first mode of vibration, here your air molecules are going to vibrate. So one end of the tube is having a length L. One end of the tube is closed so that and node will be formed at the closed end. At the open end, you will have an antinode. So L is the length of the tube, and this length will be lambda 1 by 4 because the distance between a node and an antinode is 1/4 of the wavelength. Or I can say lambda 1 is equal to 4L. Right, boys? Next, what does your wave equation tells you? Wave equation gives you V is equal to nu1 lambda 1, or I can write nu1 is equal to V by lambda 1. So let me mark this as equation 1. This let me mark as equation 2. So but the velocity of longitudinal waves of the sound waves, V is equal to root of gamma P divided by rho. So let me mark this as equation 3. Now let us substitute. So substituting 3 and 1 in equation 2. So I can go for frequency nu1 is equal to V by lambda 1. So nu1 becomes equal to 1 by 4L root of gamma P divided by rho. So this is what we call it as the first harmonic. Copy down this.
Ma'am.
Yes.
Ma'am, like in this for the stationary wave,
Hmm.
there are two wave superposition, right? So,
Correct, correct.
so in the diagram, is there only one?
Yeah. One is the incident wave, the other one will be a reflected wave.
Okay, ma'am. Okay.
This will be, if this is your incident wave, the other one will be your reflected wave.
Ma'am, gamma and mu are different, right?
Gamma is, mu is, if at all they use mu is mass per unit length. Gamma is Cp by C. So gamma is equal to Cp by Cv. P is the pressure and rho is the density. Density of the medium, that is your air will be your medium.
Ma'am, can you explain how you got the L again?
L, okay, boys. The distance between,
the
see, L is the length of the tube. L is the length of the tube. Now, in terms of wavelength, the distance between a node and an antinode is always 1/4 of the wavelength, right? Always, this is the closed end. So, whenever you have a closed end, you will get a node Whenever you have an open end, you'll get an antinode.
Ma'am, so the open end is always an antinode.
Antinode, always a node, antinode open end, closed end, it will be a node.
All right, ma'am.
Ma'am, one antinode will always be between two nodes, right?
One antinode, yeah, you can have. When we go for the next mode of vibration, you will understand what.
No, I'm asking because how do you know it's 1/4 again? Like the distance between
No,
node and antinode?
always distance between alternate nodes will be lambda by 2.
Okay. Yes, ma'am. Then okay, then it's lambda by 4. Fine.
So this is a standard one. Between a node and the antinode, lambda by 4. Between a node and node, lambda by 2. Right? Between three nodes, it will be lambda.
Navik, can you explain that again?
Okay, I'll go for the next slide and do. Boys, shall I go for the next slide and do? What is lambda? What is lambda by 2?
Okay, bye.
Shall I go for the next one? Boys, diagrams are important. You have to copy down the diagram. Shall we go for boys for the next one?
Sure, ma'am. Like,
One second. Someone was asking. Sorry. Because between, one second, suppose if I have a wave, so you have a node, and a node. Now the distance between, this is one complete oscillation. So the distance between three nodes, this was, that will become your wavelength lambda, right? For a wave, this is one complete oscillation. The distance traveled in one complete oscillation is your wavelength. Clear? So that is, so this becomes lambda by 2, half the way between a node and a node is lambda by 2. Is that clear, boys? So if I have a node, if this distance is lambda by 2, then what about antinode, midpoint? Antinode will be the midpoint. So in that case, this will be lambda by 4. Yes or no, boys? Between a node and an antinode. Because between two nodes, this is lambda by 4. Because between two nodes, the distance is lambda by 2. Look at this. Between node and node, one complete oscillation, the distance is lambda. Between two nodes, because this node is halfway between, so it becomes lambda by 2. Are you clear, boys?
Yes, ma'am.
Okay. So, but you have to be very clear with this. If you go wrong, then it will be a problem. Should I make you to write these basic things somewhere the side column? Boss, please, if you're still having a doubt, please do this. Right, boss? So this entire distance is lambda. Then between two nodes, it is lambda by 2. Then between a node and an antinode, it is lambda by 4. Is that fine? It can happen for antinode, antinode, and an antinode. It can happen, the distance between two antinodes is also lambda by 2. So make a note of it. Now look at this diagram. The length of the tube is L. Now from a node to a node, what is the distance, boys? From a node to a node is lambda 2 by 2. Correct? Then the distance between node and antinode, it is lambda 2 by 4. Because 1/4 of the wavelength, correct?
Yes, ma'am.
So what we will do is erase this. So I'll go for lambda 2. So now here your length becomes equal to lambda 2 by 2 plus lambda 4 by lambda 2 by 4. Is that clear, boys? So if you calculate, this becomes 3 lambda 2 by 4. Yeah, that's what the length is, 3 lambda 2 by 4. So what is lambda 2 then? Lambda 2 will be equal to 4 by 3L. So this becomes your equation 1. So what is your wave equation? The velocity of the wave is equal to nu2 lambda 2. So what is nu2? Nu2 is v by lambda 2. So make this as equation 2. What is the velocity?
Right.
Which one?
Ma'am, that lambda one you have, which you had given.
This one? Right now what I'm writing or what you want to know? This, what I'm writing on the rightmost part of the screen, is that
Yes,
so?
ma'am. Yes, ma'am. That yes, ma'am.
Node, node, and node. So this total distance will be lambda always. It can be an antinode also. Antinode, antinode, and antinode. Next, node and node. It will be lambda by 2. Between a node and an antinode, lambda by 4. If you know this, you can do the rest. So velocity of the wave v is equal, velocity v is equal, v is equal to root of gamma p divided by rho. So substituting 3 and 1 in equation 2. So I can write nu2 frequency, nu2 is equal to, what is v? Lambda 2 will become 4 by 3L root of gamma p by rho, 3 by 4L, 3 by 4L gamma p by rho. This is called not the second harmonic, it is called third harmonic. The reason is third harmonic. The reason is nu2 is 3 times nu1. where nu1 is the fundamental or the first harmonic. Nu1 is the fundamental or the first harmonic. So in all the other previous case, nu2 was second harmonic because nu2 was 2 times nu1, but here nu2 is 3 times nu1, so it is called the third harmonic.
Ma'am.
Yes.
And before we did the open-ended pipe, we did one derivation for the 3 modes. So that's in a wire, like the waves in a
No,
wire.
that was in a tube where both the ends were open.
Yes, ma'am. But before that,
String,
also.
the first one was a stretched string. Both the
Okay.
ends of the strings are closed. Means both the ends of the strings are fixed.
Okay, ma'am.
The string is not having any free end. Both the ends are fixed.
All right,
So
ma'am.
if it is fixed, then the wave goes and gets reflected back.
All right, ma'am.
Ma'am,
Yes.
ma'am, is this second harmonic or third harmonic?
No, this is third harmonic, not second, because look at this is 3 times the fundamental frequency, so it is
Oh, okay.
third harmonic. Next one,
Okay.
it will be third mode of vibration, you will have fifth harmonic. Those who have
Okay.
completed, those who have completed, can you draw one more pattern like this for the third mode of vibration? So you will have 3 antinodes. Can you do that? The third mode of vibration.
Ma'am, the one with the stretch string that you said, both the
Yes.
ends were fixed.
Yeah, both the ends are fixed. One end is fixed to a rigid support. The other end, you're fixing it to a load. Load means you have a weight hanger so that the wire is under tension. Only when the wire is under tension, it can vibrate. So both the ends are fixed. There is no loose end, open end of the string.
All right, ma'am.
Can we go for third mode of vibration?
Ma'am, when both the ends are free, like in a flute, right? So,
Yes, correct.
yeah, so there will be waves of the in air as an air column, right? So,
Correct.
when we
Where-
close one hole of a flute, it will act as a node, right?
Yeah, there it will make a difference. So that's why you get a different sound when you close all those holes. You change, right? You are changing the mode of vibration when you're closing one of, as you close the holes, you're changing the mode of vibration. Then you'll hear a different pitch sound. Frequency will change.
Yes, ma'am. So
So
that
that is
means
how.
in that case, second mode of vibration will be two mu one or three mu one.
Yeah, yeah. In that case, it changes accordingly. How far those holes perforations are being made. So
Okay.
all those things will take into consideration boys. That's the reason you get a different pitch sound waves.
Ma'am,
Shall
for
I
the
go for?
third mode of vibration, there will be
I'll go for the
3
third
antennas.
mode. Yes, shall I go 1 second? Third mode of vibration. Are you getting this? Just check boys. Third mode of vibration. 3 antinodes. So the distance between 3 nodes, 1, 2, and 3. The distance between 3 nodes is lambda 3. Then antinode and a node, lambda 3 by 4. Yes, are you able to understand? The distance between a node, and a node. The distance between them is lambda 3. That's wavelength. Then the distance between a node and an antinode. That will be lambda 3 by 4th, 1/4 of the wavelength. So your total L will be equal to lambda 3 plus lambda 3 by 4. Is that correct, boys? B. I need to complete
Yes.
the portion today, boys. This, at least this chapter. Only what is left for us, it's beats. And this happens to be 5 times the fundamental frequency. So that is why it is called fifth harmonic. Now, if you go for the ratio, nu1 is to nu2 is to nu3, that is 1 is to 3 is to 5. Complete your work, boys, because these are the one of this chapter where you will be tested for theory-based questions. You have to draw the diagram, then you have to derive an expression. Eleventh standard.
Yes, ma'am.
Have you completed, boys?
Ma'am, 1 minute. Just ma'am, you can move it. Put it in the chat.
Yes. Have you completed, boys?
Yes.
Others?
Yes, ma'am.
Yes, ma'am.
So should I put this in the chat box?
Siddharth, put it.
Boys, the last topic is what we call it as beats. Now,
ma'am?
before I go for the, yes?
Ma'am, can you upload the oscillations PPT?
Yeah, so yeah, you have told, I'll do that, boys. Because
okay.
certain slides which is repeating, I have to remove, that's it. I know,
okay,
I'll
ma'am.
do that. Now we'll see what you mean by beats. Now, this principle of beats is used in mining industries as well as in acoustics, right? Sound related. Anyone going for mining industries? So you should be familiar with beats. Now, what do you mean by beats? Now, suppose you have a wave which is having a frequency of say 40 hertz, right? Now, this is progressing through a medium. Say simultaneously another wave which is slightly of varying frequency. The first one was 40 hertz, the other one is 50 hertz. So when two waves of slightly nearing frequency is going to travel through a medium, right? Now look what is going to happen. This is the resultant wave. This is wave 1. The other one is wave 2. Both have slightly different frequency. When they overlap, as they progress through a medium, they overlap. And look at the resultant wave. Now the amplitude of the resultant wave, is the amplitude of the resultant wave a constant? So look at the first wave. As the first wave travels to the, is that the amplitude of the wave is changing? Anyway, can you see the change in the amplitude? You know what is amplitude? This is the maximum displacement. So when wave 1 separately progresses through a medium, there is no change in its amplitude. Same way for wave 2 also. There is no change in its amplitude. But when both the waves are passing through the medium simultaneously, look at the resultant wave. Is the amplitude of the wave the same? Boys, is the amplitude of the wave the same?
No, ma'am, it's changing.
No, ma'am.
It's changing. You can see at these points, amplitude is less. At these points, the amplitude is less. Your amplitude is directly proportional to your amplitude squared is directly proportional to the intensity, which means at some region, the amplitude is very less, almost zero, so that the intensity of the sound wave, which means the energy of the sound is very less. But at certain region, you can see this region. At this region, the amplitude is very high, which means your sound is very loud. At some region, your sound wave, right? Your sound wave, here the sound is loud, here the sound is soft. Again,
Is this neutral?
same one was. Again, you have a soft sound. So now what happens is that when two waves of slightly different frequency, when simultaneously pass through the medium, then you have a resultant wave. So that at one point, periodically it will be loud and periodically it will be soft. So this type of propagation, we call them as a beat. As beats, I'll go for the video presentation, I think so you might.
Ma'am, just one
Just
doubt
trying.
before the echo starts.
Okay.
Ma'am,
Yes,
it
no.
means loud and soft, or means like the pitch
See,
and
no
gruff?
pitch in that sense. No, you can't say about the pitch. Pitch means it will be very sharp, right? Amplitude means more energy, so the sound will be loud or it will be soft. So that relates to the intensity or the energy. Pitch means the wave should be very closer to each other. It will be very sharp, shrilling sound. That is connected to frequency. Pitch is connected to frequency. How loud the sound is, how much energy the sound carries, that depends upon the amplitude. The amplitude is very high. Yes. Is what happened.
Ma'am, like the two waves are traveling in the same direction.
Yeah, it can travel in the same direction or it can move in the other direction. That doesn't matter.
All right, ma'am.
Okay, fine. I'll just once again I'll reshare this. But if microphones are your microphone are in high decibels, just hearing thing, just reduce the sound. I don't know because here you can hear high pitch sound. That's the just keep your.
Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 117. It's on beats. Beats changes in amplitude when you have two waves that have a frequency that's very close together. And you can actually play around with this if you're connected to the internet. And so I'll put a link to this down below. But if you go to this website right here and you launch it, what you can do is you can play a tone. And so what I'm going to do is play one that's at 440 hertz. I'm then going to launch another tab, and in that tab I'm going to briefly change what note I'm playing. So that's 440 hertz. That's also 440 hertz, but listen what happens when I change one of them. Those are beats. Now they're gone. Now as I go above it, you can hear the beats again. And as I bring them back to the same value, then it goes away. Now, when would this be useful? Well, let's say you're tuning your guitar. What you can do is tune one of the string. So make sure you tune that to a tuner or a piano or something like that. Once you have that, then you can play another string. You have to move up on the fret, but play another string. And if it's close, you'll hear the beats. And if it's exactly the same, you can adjust the one, then the beats will go away. And then you can move on to the next string and the next string and the next string. And so waves, when they come together, will interact. And as they interact, they cause interference. Now that interference can be constructive, sometimes building up the wave or the summation of the waves, and sometimes it's destructive, it's tearing it down. But if those waves are very similar in frequency, what you get are these beats, and beats are going to be amplitude changes. In other words, the volume is going to go up and down and up and down and up and down due to this constructive and destructive interference. Now, it's really easy to calculate the frequency of the beats. All you do is frequency of the beat equals the absolute value of the difference between the two frequencies. So if I know frequency 1 and 2, I simply subtract 1, and it's the value, absolute value of those. And so again, in review, if you don't know what constructive and destructive interference are, if we have two waves that are perfectly the same frequency and they're right next to each other, what we'll get is constructive interference. If they're out of phase with one another, we'll have destructive interference. But if the frequencies are slightly off, and if we look at this animation down here, these are frequencies that are close but not exactly the same. What you get is, as you have this constructive and destructive interference, you get the blue summation of those two waves, and you can see that we're seeing these changes in the amplitude. In other words, the amplitude is decreasing, then increasing, and then decreasing. Now, if I could make those frequencies exactly the same, then the beats are simply going to go away. How do you calculate it? Again, it's frequency 1 minus frequency 2. Absolute value of. And let's do a sample of that. So I'm using Audacity. It's a little music software. And so what I'm going to do is I'm going to generate some tones. And so I'm going to generate a 440 hertz tone. So that'll be in one track. And then I'm going to add another track down here, and we're going to generate another tone. So we'll make this one slightly different. It's 440 hertz, like that. Now let me mute the bottom one and play the top. And now let me mute the top and play the bottom. So they sound almost the same, but let's play them together now. So we'll unmute them. So now you can hear those beats or those changes in the amplitude. Now let's calculate what the frequency of the beat should be. So frequency of the beat is going to be F1 minus F2. And so what were the two frequencies? Well, we had 440 and 444. And so if I put those two values in, what's my frequency of the beat going to be? It's simply going to be 4 hertz. So now let's check that with this model. And so what I'm going to do is now mix these two together, and we're making a single track of the two. And now let me get rid of those first two tracks. You can already see the beats. And now let's check our numbers. So let's look at 1 second in time. It's exactly 4 beats. The frequency of the beats equals the difference between the two frequencies. So did you learn to use a visual representation to explain how slightly different frequencies cause beats? I hope so, and I hope that was helpful.
Let's just check. It's time. Your other class started? Boys?
Ma'am,
Siddharth? Yes, your other class has started?
I'm not sure, ma'am. 1 minute.
No, ma'am, not yet.
I think so. It's time up. It's 1:15 right now. I think only one slide is left, boys. I think you can leave. We have a practical period right now. It's one, right? Let me check. Numericals are left in this chapter. I'll do numericals as we proceed with the other chapter also. I think it's time 1:10. I have other class, practicals class. So you can leave.
Thank you, ma'am.